Hey guys, so in this video, we're going to talk all about linearizing graphs. This is a really important skill on the AP Physics exam, whether you're taking AP Physics 1, AP Physics C Mechanics, really any of the AP courses, you are going to have a question on the AP exam that requires you to do something with graphing, and linearizing graphs often comes up. So this is an important skill to have. So I'm going to walk you through exactly how you would linearize a graph depending on which graph shape you have, and how once you have a linearized graph, you can use that to figure out other things and what types of questions you're going to get asked based on having linearized a graph. So let's go ahead and get into this here. The first thing that I want to talk about is the four main graph shapes that you need to be able to recognize. And these are all important to know. These are the most common ones that you're going to see if you have, whether you are actually like looking at a graph that's been given to you, or if you have to actually plot the points and make the graph yourself, it's going to be one of these types of graphs. So know the graph shapes. So number one is our good old friend, the linear graph. This one, of course, we just have a straight line, usually positive slope, maybe a negative slope, but it's just a straight line. The other option here is we are going to have a quadratic graph, or one that has this parabolic type shape. The third one is the graph of like square root of x, a square root graph. So that one's going to look like this. And then an inverse square graph is going to look a little bit more like this. And we'll go through some examples of where exactly these graph shapes would show up based on some of the equations that we have in AP Physics 1. But before we move on from here, I also want to talk about proportionalities a little bit, because proportionalities are really what's going to get you from the graph shape that you have to a linearized graph. So you're probably familiar with the equations for these types of graphs, or like functions that would match up with each graph shape. But you may not be as familiar with the idea of a proportionality. I can't talk today. So let's talk a little bit about what that means. If you have an equation, you have something in the format like y equals mx plus b, for example, for a linear equation. Or for a quadratic equation, you have y equals ax squared plus bx plus c. So those are equations because you have an equal sign in them. So what's on the left is equal to what's on the right. But when we write a proportionality and we say what's on the left is proportional to what's on the right, we're stating that there's a relationship there, but it's not an equality. But if we change in some way, like we double or triple or cut in half what's on the right-hand side, that is also going to affect what's on the left-hand side. So it's saying that there's a dependency among the two things that are in that proportionality. So for a linear equation, we can kind of boil that down to a proportionality that says y is proportional to x. Maybe they're not equal, but they still depend on each other. In a quadratic equation, y is proportional to x squared. For our square root graph, we can say y is proportional to the square root of x. And in our inverse square graph, y is proportional to 1 over x squared. All right, so again, we see these relationships come up in the equations that we use for AP Physics 1. Typically, well, this one's like not as common as the other ones, but it still can definitely come up. I'll show you an example of that. But we definitely want to draw these proportionalities based on our graph shape, because what we're going to see is that if we then create a graph of y versus x, that's a linear graph anyway. If we graph y versus x squared, that is going to linearize our quadratic graph. So if we graph, for example, position and time, and we get this kind of graph, if we graph position and time squared, we're going to get a linearized graph. All right, so, and again here, let's follow up here with our square root and inverse square. If we graph our y value versus the square root of x, that's going to linearize our graph, or create a graph where we get a straight line. And then y versus 1 over x squared, that is going to linearize that graph. We're going to end up with a graph that is a straight line, and we have linearized it. All right, so let's take a look at a couple of examples. And I want to start off here with two examples where you would just see linear relationships. And if it's already linear, you don't have to linearize it. I just want to give you some quick examples here. So if you have a graph of constant velocity motion and you're graphing position and time. So position, and I'm writing position like the x for position, not x as in the x-axis here. So if I graph position in meters versus time in seconds for constant velocity, I am going to get a linear graph. Okay, there is a linear relationship between position and time in this case. So position is proportional to time. If I graph acceleration and net force, like in Newton's second law, so acceleration in meters per second squared, and net force in newtons, again, I'm going to have a linear graph here, which tells me that the acceleration is proportional to the net force. And those are just examples of linear graphs, nothing to do there, but I just want to illustrate here for a second this idea of the proportionality and how that matches up to our linear graphs. So let's take a look at an example where we do not have a linear relationship like already to start. So one example would be a position in time graph where we have constant acceleration rather than constant velocity. So if I graph position in time and my graph looks like this, looks like have a parabola, that means that I have a relationship such that position, and again, that's on my y-axis here, so position in meters and time in seconds, the position is proportional to time squared. So if I were to graph position versus time squared and put, again, position on the y-axis and time squared, the unit for that would be second squared, on the x-axis, that is going to give me a linear graph. So I have linearized a position in time graph by graphing position versus time squared. Okay, so see how coming up with this proportionality is going to help you. It's kind of like the direct line to your linearized graph. This also happens, so say we're graphing kinetic energy and velocity. So if I'm graphing kinetic energy and velocity, so kinetic energy in joules on my y-axis, velocity in meters per second on my x-axis, this is going to be a graph shape where I'm getting a quadratic relationship because, okay, and I want to show you this too to kind of like bring together how we're getting something squared here. Remember, kinetic energy is equal to 1/2 mv squared. So my graph is showing that kinetic energy is proportional to the speed squared. So if I graph kinetic energy on my x-axis and speed squared, or did I just say x-axis? If I graph kinetic energy on my y-axis and speed squared on the x-axis, that is going to linearize my graph. So if I put kinetic energy in joules, speed squared would be meters squared, seconds squared, I'm going to get a graph that is a straight line. Okay, it all comes back to that proportionality. If we do this on our y-axis, this on our x-axis, we're going to get that linearized graph. All right, so that's two examples with quadratic relationships that, that we have linearized. And two, I'll come back for a second here. So this position in time graph, so notice here, position let's assume initial velocity is 0, 1/2 at squared. So we have x and t squared. So that's where our proportionality, x is proportional to t squared. That's kind of like validates what we have there. So moving along, let's take a look at some square root relationships here. So period of a pendulum and the length of a pendulum, if we were to graph those against each other, so period in seconds, length in meters, we are going to get a graph that looks like this, like the graph of square root of x. And if we look at that graph, we want to recognize that square root of x shape to be able to say that the period is proportional to the square root of the length. And that we can kind of validate that by remembering that we have this equation where the period is equal to 2 pi times the square root of L over G. So if we kind of like cut out the 2 pi and the G, switch our equal sign to a proportionality sign, we come up with this proportionality here. So now if I put this on my y-axis and this on my x-axis so that I have t and the square root of L, I am going to have this linearized version of my graph. Okay, I also want to mention too, another way that we could graph this and also have a linearized graph is graphing. So if I were to square this square root of L and also square t, I could also graph, an alternative here would be to graph t squared on the y-axis and L on the x-axis. So that's just like squaring all of the quantities. That would be another way to write that graph, and it would also be linearized. Okay, so speed of a fluid and height. So coming in here with a fluid equation, if you recall here, so V square root of 2g, so we have Torricelli's theorem. Here we have V proportional to the square root of h. So if we were to graph the velocity and height, we are going to get that square root of x shaped graph. So if we graph now v and the square root of h, or height and v squared, both of those options here have the same effect. They're going to linearize our graph. We're going to get a graph that is a straight line. If we graph now v squared and height, or v and square root of h. Okay, so again, it all comes back to the proportionalities. Don't forget how to do this. That's super, super important. So our last example here, let's take a look at some examples of that inverse square relationship. So if we're talking about a graph where we have our gravitational force on our y-axis, and the distance between two objects, so this would be like Newton's law of universal gravitation, we are going to get that classic inverse square graph. Looks pretty much like this. So what that graph shape tells me is that this gravitational force is proportional to the inverse square of distance. And if I look at the equation that relates these two things to each other, I have gravitational force, and if we kind of like ignore these things here, just focus on the relationship with r, we have 1 over r squared on the right-hand side. So if I graph force, the gravitational force, and 1 over r squared, that is going to linearize my graph. If I do that. So also here again, we have the same exact kind of relationship. Again, like electric force and distance is another relationship between a field force and distance. So we have the same thing. So if you were to graph the electric field force and distance, we're going to get that inverse, ooh, ugly one, inverse square graph. We have an equation that validates that for us. So that would be Coulomb's law, K, Q1, Q2 over R squared. Electrostatic force is proportional to 1 over R squared. So if we graph electrostatic force on our y-axis and 1 over R squared on our x-axis, we're going to get that linearized graph. All right, so hopefully in general that helps you see like how we can get from a certain graph shape, and it doesn't matter what it is, like maybe it's an equation that you're familiar with, maybe it's an equation that's on the equation sheet, or maybe it's not. Maybe it's an equation that you're trying to come up with based on relationships between quantities, and it's one that you're not necessarily familiar with, but regardless, you can still build this linearized graph by recognizing these three, like besides linear, the three other graph shapes, the quadratic relationship and square root and inverse square. So those you want to be able to recognize those. So let's take a look here. I want to show you one example of how you can actually use your linearized graph. Like what kinds of questions might be asked where now it's like, okay, you've created a graph, you've linearized a graph, but what can we do with that to figure something else out? Like what kinds of questions are they going to ask you? Okay, so let's say, for example, we have some data on the period of a pendulum, or the period of a mass spring system and the mass of that mass spring system. So we've collected our data. Maybe we've even written a procedure on like one of those lab-based FRQs. If you're having trouble with lab-based FRQs, by the way, guys, I actually also have a video on that. So if you're struggling with those, I have 4 super important tips that will help you with figuring out lab-based questions. So going over how to write a good procedure, making sure you get all your points there, how to use and kind of like integrate equations to help you figure stuff out, some other important stuff about graphing, and then looking for ways to explain experimental errors. So if you're getting like variations in your answer there. But anyway, so coming back to this here, so if we have a graph, maybe we have measured the period of the mass spring system, we've like timed it out, we know what the mass is, and we've switched, like we start with 0.1 kilograms for mass, and then we go to 0.2 and 0.3 and so on and so forth, and we've graphed the period versus the mass. So this we would expect to find that our graph is consistent with a graph of the square root of x. So what this tells us here is that the period of this mass spring system is proportional to the square root of the mass. And if we look at the equation that we have that relates those two things, 2 pi square root of the mass over the spring constant, that is consistent with an equation that we are familiar with already. So that fully makes sense. So then if we were to linearize that graph and have a graph of t and square root of the mass, or t squared and mass, both are fine, that would give us a graph that is a linearized graph. We have a straight line. So we have a slope here that is constant. So the importance of having a constant slope like this is slopes of graphs in physics are very, very meaningful, as is the area under the graph. But in this case, it's more so the slope. So in a question like this, you could be asked something like, based on the information that you have here, what is the spring constant of this spring? And if you have a whole data table that you've used to graph multiple points, you don't want to just like use this equation, pick one of your masses and one of the periods and plug it in and solve for K. You don't want to do that. Instead, you want to use all of your data to come up with this value. You don't want to just pick one random, like don't just pick the first one or the last one or like whatever random one in the middle. The way that we can use all of our data to figure this out is to come up with an equation or an expression for the slope, and that is going to help you figure out the spring constant here. So if I consider here finding the slope of this graph, so let's say I have a few data points and I've drawn Make sure it seems like a linear relationship here. And I've drawn my trend line. All right. I have this linearized graph. I have my trend line. So we want to make sure, first of all, that you pick, for finding your slope, 2 points that are on your trend line. So I might pick, for example, because they lie on the trend line, this point here and this point here, and I find my slope. So we know that the slope of a line, sorry, I don't want to use mass. I'm gonna write out slope because I don't want to get confused between slope and mass. So our slope in general is going to be the change in our y-axis quantities over the change in our x-axis quantities. So here's where we're picking 2 points and finding the change in y over the change in x. But just to be clear here, if we graph t and the square root of m, I have t on my y-axis and square root of m on my x-axis, okay? So let's make this actually even a little bit simpler. I'll walk you through it and then we'll make this a little bit simpler. I'll tell you why. So if I were to take this equation here, the equation that we know, and kind of like rework this so that it's in the format where on one side we have t over the square root of m, and on the other side we have all the other stuff, here's what it's going to look like. So t 2 pi, the square root of m over k is the same thing as saying the square root of m over the square root of k. So t over the square root of m is equal to 2 pi over the square root of k. All right, so where that's going to help me here is I could be asked something like, again, I want to know what the spring constant is for this situation here. If I have my slope, I now have a way to solve for the square root of k. All right, so that would help me get the spring constant for this situation here. All right, so being able to look for this y equals mx plus b setup, or finding the slope of your graph and being able to recognize here either the units will tell you what your slope means, or reworking an equation that you already have so that it's set up in a way that you have some kind of set up on the right for slope, and then seeing what's on the other side can help you find other unknowns that you may be asked for. So in this case, spring constant. All right. So just another quick side note related to that is we do want to always look, if we have a linearized graph, for that y equals mx plus b setup, so that we can see what's on our y-axis, what's on our x-axis, and then what does our slope represent. A lot of times our y-intercept will be 0. All right, guys, so I hope that helps you here. Like I said, this is something that's going to show up on usually those lab-based free response questions. So make sure you're able to linearize your graphs, and this is how we're going to do it. We're going to write proportionalities, graph the y versus x, and that's going to give you your linearized graph. So I hope that's helpful as the AP test is coming up. So take a look, make sure you subscribe. I'm going to be sending out some more videos that are going to help you with all of these little details for doing awesome on your AP exam. All right, I'll see you in the next one.